Okay, hello everyone in a new video. So we have reached part 4 of chapter 7, which is the chapter of the voltage of the mains in the second unit of electricity. And in this one we'll complete solving the exercises related to this chapter. Then exercise number 6, they are telling us the electrical installation in a kitchen is fed by sinusoidal alternating voltage of effective value U is equal to 220 volts. So here, even if they didn't denote this U by the effective, but it is the effective voltage because it is the one that makes the effects, and we will use it in different formulas related to power, Ohm's law, etc. whenever needed. This installation includes the following electric appliances. So we have a refrigerator, a washing machine, an electric water heater which can be considered as a resistor of power P is equal to 1540 watts. So the moment they mentioned it is a resistor, simply we can apply Ohm's law. And an incandescent lamp carrying the following indications: 220 volts, 100 watts. Number 1. They are telling us these electric appliances are connected in parallel. Why? So these electric appliances are a part of a domestic installation, then they are connected in parallel in order to function independently, and this is very important. Okay, so always electric appliances in a domestic installation are connected in parallel in order to function independently. So in order to function independently. Now number 2, the lamp functions normally. Why? So here they are talking about the lamp, about the incandescent lamp that has a rated voltage which is given by 220 volts, and you know that the applied voltage is given by 220 volts. So whenever we need to discuss the functioning of an electric component, we should compare the rated to the applied. Then since the applied voltage is equal to the rated voltage of the lamp, and between the brackets this is given by 220 volts is equal to 120 volts, then the lamp functions normally. So this is 2.1. Now in 2.2, calculate the effective current, electric current I1 through the lamp. So we know that the lamp is functioning normally, and in this case we can use the indications. So we have the voltage and we have the power, and we know that the missing indication is given by the current. So knowing that P is equal to U multiplied by I, and we are interested in determining the value of I, then constructing the triangle or setting up the triangle, covering with our hand the value of I, then I is given by P divided by U. The current is denoted by I1. The value of P is given by 100, and the value of the voltage is given by 220. Plugging this on the calculator, we get the value of the current rounded to the nearest second degree is given by 0.45. Since everything is expressed in the SI, and in particular P and U, then the value of I1 will be in the SI, which is amperes. Then I1 is equal to 0.45 amperes. Now in 3.1, the effective voltage across the water heater is 220 volts. Why? So notice that all of these appliances are connected in parallel, which means that they have the same voltage. So because the water heater is connected in parallel with the voltage source, so for this reason the applied voltage will be 220 volts, and this is given by the law of uniqueness of voltages. Let me say the water heater is connected in parallel. Then according to the law of uniqueness of voltages, it has the same voltage, and it's given by U is equal to 220 volts. Now notice that in this case we have three different questions that are related to the same idea. If they are asking us why they are connected in parallel, we say in order to function independently. If they are asking us about the functioning of the lamp, we compare the rated to the apply. If they are asking us why it is 220 volts, because it is connected in parallel. Here we cannot say because it's functioning normally, because we don't know the rated voltage of the water heater. In fact, all of these appliances will function under a voltage to 120 volts. Now as for 3.2, calculate the effective current I2 through the water heater. So here let me say that I1 is given by 0.45 amperes, and we are interested in calculating I2 across the water heater. Now what is the given? The water heater, which can be considered as a resistor, has a power given by 1450 watts. Then using the same formula here, P is equal to U multiplied by I. Covering I, then I is given by P divided by U. So this is I2. And then the power is given by 1540 divided by 220. Plugging this on the calculator, we get that the current traversing the water heater under normal functioning is given by 7 amperes. Then I2 is equal to 7 amperes. And let me write it down here. So yet we didn't use this statement. It's okay. Now in number 4, knowing that under normal functioning the effective electric current through the refrigerator and the washing machine are respectively I3 and I4. So the refrigerator corresponding for I3, which is equal to 5 amperes, and the washing machine is 10 amperes. Determine the effective main electric current when all the given electric appliances function at the same time. So we know that the main electric current in such cases or in the domestic installation can be given by I main is equal to the total power divided by U effective. But since they are since we don't have the electric power of each of the following components, however, we have the currents that are given by I1, I2, I3 and I4. Knowing that they are connected in parallel, then we can simply apply the law of addition of currents. And say that the main current is equal to I1 plus I2 plus I3 plus I4. Why these? Because the domestic installation consists of the lamp, the water heater, the refrigerator, and the washing machine. Then simply we can add the currents. So 0.45 plus 7 plus 5 plus 10. Now plugging these on the calculator, Then the main current traversing this domestic insulation is given by 22.45 amperes. Then the main current Now, in number 5, they are telling us we intend to protect these electric appliances with a circuit breaker. Which one of the three available circuit breakers rated at 25, 30, and 40 amperes is the most adequate to be used in this kitchen? Why? So, by the most adequate means convenient. Then, in order to determine the convenient circuit breaker, let's refer to the definition which is given by the most convenient circuit breaker or the most adequate. Is the one having rated current slightly greater than the traverse current or than the main current. All of these, as you can notice, 25, 30, and 40, all of these are greater than 22.4, 22.45, but by the slightly we means the closest. So greater and the closest, which corresponds to 25 amperes. Now moving to the next exercise, which is exercise number 7. And the object of this exercise is to show evidence of the role of a fuse in an electric apparatus and adapter. So here in this document 1, we have the adapter. So this adapter may correspond to the one of the phone or even the laptop. For this, we consider the circuit whose diagram is represented. Document 1, they mentioned document 1, now we can use it. It is formed of an ammeter A and two resistors R1 and R2 of respective resistances. R1 is equal to 18 ohms and R2 is equal to 12 ohms. Connected in series across the output of the adapter. Now let me explain the circuit. So this is the plug which is connected, for example, to the wall outlet. So here the voltage is given by 220 volts and it is AC sinusoidal. The role of the adapter to modify this voltage, and it will supply voltage to the given circuit. Now the adapter bears the following inscriptions for the input: 220 volts, 50 Hz, and this symbol stands for AC sinusoidal. So here this is the input and this is the output. Then the input must be 220 volts, 50 Hz, and AC sinusoidal. And for the output 9 volts, the output circuit of this adapter is protected by fuse marked for 100 milliamps. Then the fuse is marked by the following indication. Here there is a missing indication, which is this. Now this means a DC voltage. Usually DC voltage is denoted by this, but this is another indication for a DC voltage. Now in number 1, they are telling me what does each of the three indications inscribed on the input of the adapter represent. These are the input. So remember that the adapter is an electric component which functions when it is fed by such type of voltage. So what does 220 volts represent? Rated voltage of the adapter under which it functions normally. Hz rated frequency of the adapter under which it functions normally. Now it is left this indication. Now the type of voltage, which is given by between the brackets AC sinusoidal, under which it functions normally. Okay. Now in number 2, in order to feed the circuit with a 9 volts DC, we must connect the input of the adapter across the mains to justify. So this is the circuit. In order for the circuit to be fed by 9 volts DC, which is this, the output here, or the input, and this is the output, the input must be across the mains. Why? Because so this must be connected to the wall outlet of the mains, which is this. So this must be plugged here. Now why? Because we know that the voltage of the main supply to 120 volts, 50 hertz, and it is AC sinusoidal. So let's say since the voltage of the mains supply AC sinusoidal voltage source of effective voltage 220 volts and of frequency 50 hertz. And in this case, the adapter will function normally. When it's functioning normally, the output it will be a 9 volts DC voltage. Now in number 3, they are telling us calculate the resistance of the resistor equivalent to R1 and R2. So notice that in this case R1 and R2 are in series. Then because they are in series, then the equivalent resistance is given by the sum, which is equal to 18 plus 12, which is equal to 30. Since both R1 and R2 are expressed in ohms, so the value of R equivalent will be in ohms. So R equivalent is equal to 30 ohms. And as we mentioned previously, that whenever we calculate an equivalent resistance, we need to redraw the circuit. Here I will not redraw the circuit because, okay, let me redraw it. So this is the adapter. This is the wall plug like this. Now this is the resistor replacing both of them. This is the ammeter connected back to the adapter. Then we are in part 4. Now determine the current carried by the circuit. In order to determine the current, so we have two different laws. Either we use the law of addition of currents, but here we don't have different branches in this circuit. The only law that we are left with is given by Ohm's law. Then apply Ohm's law to R equivalent. and Ohm's law is given by U is equal to R multiplied by I. We are interested in determining the value of I. Then covering our hand over I is given by U divided by R. So here for sure we are using this circuit, otherwise why we have calculated R equivalent. And now what is the voltage? Notice that the adapter must be supplied by voltage given by 220 volts AC sinusoidal, but the voltage leaving the adapter will be 9 volts and it is DC. And because the R equivalent is the only resistor in this circuit, the ammeter doesn't take any voltage, so the voltage of the resistor is given by 9 volts. Now plugging this fraction on the calculator, we will obtain 0.3 since both U and R are expressed in the SI, so the value of I will be in the SI, which is amperes. So the current now traversing the circuit is given by 0.3 amperes. And here let's recall that this circuit is protected by a fuse. So notice that the current traversing the circuit is given by 0.3, which is equal to 300 milliamps. Now here nothing will happen because the fuse has a rated current which is given by 400 milliamps, whereas the current traversing the circuit is equal to I is given by 300 milliamps, and since the traverse current is less than the rated current of the fuse, nothing will happen. Now in number 5, they are telling us the resistor of resistance R2 is short-circuited. So now, because we have made a changement in the circuit, then we should erase this one. And by short-circuiting R2, it means that R2 is now replaced by a connecting wire. So short-circuiting means that across R2 we have a wire in parallel. And now notice that these two electric components are in parallel, and according to the law of uniqueness of voltages, they have the same voltage, and the voltage of the wire is 0, so the voltage of R2 is 0. This is exactly as if, or equivalent to say that R2 is replaced by a wire. Now here in this case, what we have done, previously the value of the resistance equivalent to this circuit is given by 30 ohms. Now 30 ohms will decrease because we have removed one of the resistance, so the value of R decreases. Now if R decreases, we expect that the value of the current will increase, and which may affect the functioning of this circuit because it's protected by a fuse. Now let's check. Determine the new value of the current, and this can be done using Ohm's law. So the only component here present in the circuit is given by R1, given by U is equal to R multiplied by I. We are interested in determining the value of I, constructing the triangle. Then the new I, let's say, is given by I1 is equal to U divided by R. Here we are talking about the output voltage of the adapter, which is given by 9 volts, divided by the resistance of R1, which is given by 18. Now this is given by 0.5. Since everything is expressed in the SI, so the value of I1 will be in the SI, which is amperes. Then the new current traversing the circuit is given by 0.5 amperes. Now in 5.2 they are telling us the ammeter reads 0. Why? Explain then the role of the fuse. So the ammeter is reading zero current, which means that the circuit is an open circuit, and this is because now the traverse current in the circuit is given by 0.5 amperes. So I1, which is equal to 0.5 amperes. Now recall that if you want to convert from milliamps to amps, we divide by 1000. However, if you want to convert from amps to milliamps, we multiply by 1000. Then 0.5 multiplied by 1000 is equal to 500 milliamps. Why? Because we are interested in comparing the traverse current to the rated current of the fuse, and we know that in physics we cannot compare quantities unless they have the same unit. Now, why the ammeter is reading a zero current, which is equivalent to say that the circuit is an open circuit? Because now simply, since the traverse current is greater than the rated current of the fuse, so it is greater than the rated current of the fuse, and this is because 500 milliamps is greater than 400 milliamps, then the fuse will melt, cut the circuit, which means it is open circuit, stops the current, and protect other electric components. So this is the rule. So this is why the ammeter reads zero, because there is no current, and the role at the same time, which stops this current and protect other electric components, okay, from overrated current. Now let's move to the next exercise, which is exercise 8. They are telling us a house is equipped with a circuit breaker 15 amperes. The voltage of the main across one of the outlets of this house is 220 volts. We connect the heater across the outlet. The heater is formed of two resistors D1 and D2 of respective resistances R1 and R2. Number 1. The heater functions normally when D1 and D2 are connected in series. 1.1. So draw a diagram representing D1 and D2 across the outlet. So here we consider that the outlet is the voltage of the mains, which is by default AC sinusoidal. So this is the voltage supplied by the mains or the wall outlet, and these are the two resistors that are connected in series, D1 and D2. Now calculate the resistance of the resistor equivalent to D1 and D2 knowing that they are in series. Then the equivalent resistance is given by R equivalent, which is equal to R1 plus R2, which is equal to 20 plus 30. This is equal to 50. Since both R1 and R2 are expressed in ohms, so the value of R equivalent will be in ohms. And whenever we calculate an equivalent resistance, we redraw the circuit representing this equivalent resistance. So this is the AC source, this is R equivalent, and this is 220 volts. As we have said previously, that the trick in solving such type of exercises is to write the voltage on the circuit, as we have done in this case also. Now in 1.3 they are telling us calculate the current carried by the circuit. Since this is the only electric component found in the circuit and we know the applied voltage, then the current can be directly calculated using Ohm's law. then apply. We have that U is equal to R multiplied by I, and we are interested in determining the value of I. Then covering with our hand the value of I, then I is given by U divided by R. Here we are applying Ohm's law to R equivalent, and because it is the only component connected or found in this electric heater, so here we are talking about the heater. It is not water heater, it is a heater. So the voltage is given by 220 volts divided by R equivalent. R equivalent is given by 50. Now plugging this on the calculator, so the current traversing this equivalent resistance is given by 4.4 amperes. Now here we don't specify the direction of the current because we don't have positive pole or negative pole. Now in 1.4 they are telling us determine the energy consumed in the heater in 2 hours. So we know that the energy is given by E is equal to P multiplied by T. Now here, previously all the energies that we have calculated in kilowatt hour, here they didn't specify the unit of energy. We know that the SI unit of energy is given by joules. Now the time, which is equal to 2 hours, knowing that in order to convert from hours to second we need to multiply by 3600, then 2 multiplied by 3600 is equal to 7200 seconds, because previously we didn't convert hours, we kept time in hours because we were interested in a unit of energy which is given by kilowatt hour, which means that power must be given by kilowatts and time in hour. Okay, so now time must be converted to second because they didn't specify the unit, and by default the SI unit of time is given by second. So this is the time. Now in order to calculate the energy we need to determine also the power. The power is given by U is equal to P is equal to U multiplied by I. The value of P of this heater, which consists of R equivalent, has a voltage of 220, and the value of the traverse current is given by 4.4. Now plugging this on the calculator we will obtain 968. Since both U and I are expressed in the SI, so the value of P will be in the SI, which is watts. Now after we have determined the power in the SI, which is watt, and converted the time to the second in the SI, now we are ready to calculate the electric energy. So here they didn't specify which form of this energy, but for sure we are talking here about the electric energy. Then E is equal to 968 multiplied by 7200, and in this case the answer is given by 6. Since both this and this are expressed in the SI, so the value of E will be in the SI, which is joules. So E is equal to 6,969,600 joules. Now in number 2, D1 and D2 are supposed to be connected in parallel. So let me draw the circuit again. So this is D1 and this is D2. Now calculate the main current. So if you notice the previous steps, in order to calculate the main current, first we need to calculate the equivalent resistance. Now the equivalent resistance will change because the grouping changed. So D1 and D2 are in parallel. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Now the value of R1 is given by 20 and the value of R2 is given by 30. Now whenever we are adding these two fractions, we need to consider the common denominator and the simplest form of the fraction, or using the calculator, then the equivalent resistance is given by 1 over 12, not the equivalent resistance but the value of 1 over R equivalent. And now if we crisscross, or the reciprocal, which yields that R equivalent is equal to 12, since everything previously is expressed in the SI, so the value of R equivalent will be in the SI, which is ohms. But recall that the question is to calculate the main current. Now let me represent R equivalent in the corresponding circuit. Now we are ready to apply Ohm's law on R equivalent. To the new R equivalent, we can say that this is R equivalent prime, because we have used R equivalent previously. So U is equal to R multiplied by I. We are interested in determining the value of I. Covering I with our hand, then I is equal to U divided by R. Here we can say R I prime, for example, the voltage is the same, and this is R prime equivalent. Then 220 divided by 12, which is equal to 18.33. Since both this and this are expressed in the SI, so the value of R prime will be in the SI, which is amperes. Then I prime is equal to 18.33 amperes. Then explain why the circuit breaker will then open the circuit. So in order to know whether the circuit breaker will open or remain closed, we need to compare the traverse current to the rated current of the circuit breaker, which is given by 15 amperes. Then let's say since the traverse current of the circuit breaker and this is because 18.33 is greater than 15 amperes, then the circuit breaker will open the circuit. And moving to the final exercise of this part and in this chapter, exercise 9, the adjacent graph represents the variation as a function. The variation here we should be written the variation of the voltage U as function of time. Okay, so the variation as a function of time of the voltage across the terminals of the generator takes square root of 2 is equal to 1.4. Now in 1.1, is the voltage represented by the graph direct DC or triangular or alternating sinusoidal? So we know that it is alternating sinusoidal, and we can explain as usual and say since it varies with time, and the shape is given by sinusoidal. Now in 1.2 they are telling us specify a point on the graph that may be used to determine the maximum value UM of the voltage. So this is the voltage. Usually the voltage is determined by considering the center of the oscilloscope and counting the number of divisions between the center and the maximum point reached by the curve, and in this case we can consider the point A. So the point is A. And before we continue solving this exercise, the trick is to determine the values of x and y, as well as for the vertical sensitivity and the horizontal sensitivity. Here x, which is the number of divisions between two consecutive peaks. So choosing A and B, we have 1, 2, 3, 4. So x is equal to 4 divisions. As for y, the number of divisions from the center to the maximum point reached by the curve 1, 2, 3, 4. Now as for the vertical scale, which is the scale along the y-axis, notice that it is indicated here, which corresponds for each one division is equal to 77 volts, then 77 volts per division. As for the horizontal scale, this is the horizontal, they are telling us 5 milliseconds for each one division. Now, knowing that milliseconds is not the SI unit of time, in order to convert from milliseconds to seconds, we divide by 1000. So this is equal to 5 divided by 1000, which is equal to 0.005 seconds per division. So this is the horizontal sensitivity, and this is the vertical sensitivity. Now the point here is A, so this is part of the answer. And they are telling us to calculate UM. We know that UM is given by SV multiplied by Y. The value of SV is given by 77. And the value of Y is given by 4. Now plugging this on the calculator, then the maximum voltage given by this voltage source is given by 308. Since everything is expressed in the SI, so the value of UM will be in the SI, which is volts. Now as for 1.3, they are telling us name a couple of points on the graph that allows us to calculate the period T of that voltage. So the period is usually determined by first determining X that we have done. And here, since they are telling us a couple of points, it means that we need to give them 2 points. Couple means 2. Then simply the points can be A and B. One can even say C, skip a point, choose another point, C and F. So sorry, C and I. Even F and E, all of these answers are accepted. Now calculate the period and deduce the frequency F. So the period is given by VB multiplied by X, which is equal to 0.005 multiplied by X, which is given by 4. Plugging this on the calculator, then it's given by 0.02. Since everything is expressed in the SI, so the value of the period will be in the SI, which is seconds. And in the same part, they are telling us to deduce the frequency, and by deduce it means that we need to use the previous part. So the frequency is equal to 1 over the period, 1 over 0.02. So this will be given by 50. Since the period is expressed in the SI, so the value of F will be in the SI, which is Hertz. Then the frequency is given by 50 Hertz. Here, let me write that the maximum voltage is given by 308 volts. And the frequency is given by 50 Hertz. Now in 1.4, a voltmeter in the AC mode connected across the generator indicates a value U. What does U represent to the voltage across the generator? Now we know that always a voltmeter measures the effective voltage and not the maximum voltage. So whenever they are talking about voltage, in the case of AC we have two voltages, UM and U effective. always, 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 the one that makes the effect is U effective, okay? So everything that we use in case of Ohm's law, power, in anything, we are concerned about the effective voltage and not the maximum. So let me say a voltmeter in the AC mode. So because we know that a voltmeter has two modes, either AC and DC mode, measures U effective, and we are interested in calculating U effective, which is equal to UM divided by radical 2. Now the value of UM is given by 308, and the value of radical 2 is given by 1.4. Plugging this fraction on the calculator, then we have that the effective voltage is given by 220. Since UM is expressed in volts, so the value of U effective will be in volts. Now, in number 2, the voltage across a wall outlet in your house is identical to that represented by the graph, Y. So this graph have the following properties. U effective is equal to 220 volts, frequency of 50 Hertz, and it is AC sinusoidal. All of these properties are the properties of the voltage of the mains. Since the voltage represented in the graph has the same properties of the voltage of the mains that are given by 220 volts, AC sinusoidal, and frequency 50 Hertz, then it is identical to that. So then, let me say, then the voltage across then the voltage across a wall outlet is identical to that represented by the graph. So that's it for me in this video, guys. See you soon and a new one.